Hi. Today I consider some simple but already non-trivial case of a domain where we can solve the Dirichlet problem. So it is a Laplace equation in half space. So consider the following domain, which is next to the whole space. It is half space. So we have space Rn. So if x in Rn, x has coordinates x1 and so on, xn. And let us consider Rn plus equals the set of x equals x1 so on xn, such that xn more than 0. Now, in particular for n equal 2, it's already interesting case. R2 plus, it is the set of x equals x1, x2, such that x2 more or equal than 0. So this is this domain. It is x1, it is x2, and this domain, the upper half space, is a domain where we are solving the Dirichlet problem. So the problem is the following. We have to find a function u such that delta u equals f in R and plus, and the boundary, let us denote it simply R n minus 1. Gamma equals R n minus 1. It is xn equals 0. So it is n minus 1 dimensional plane in n dimensional space, this one. So u on gamma equals g, where f and g are given function. Now, if we don't want to have complication, let them be regular functions, say twice differentiable, so that and then we'll see how can we generalize it. How to solve it? So let me remind you that if you have any domain, let us domain D with boundary gamma, then and you have a general problem is Laplacian u equals f in D, u on the boundary gamma equals g, given function, then to solve this problem we have to construct the Green's function. Green's function g of x, y is a function satisfying the following condition. Laplacian with respect to y, g of x, y equals delta of x minus y. so if you have a point, the point x and y are points in our domain, and so everywhere for fixed x, everywhere beyond x, this function is harmonic, first of all. And if you say what does it mean that Laplacian is delta, this means that if you a little bit modify this function, then Laplacian will be 0 outside of small ball of radius epsilon, and the function, modified function, will be harmonic outside this epsilon, and integral of Laplacian, this modified function, over this small ball is 1. Yeah? So we can, or equivalently, if you consider the gradient of this function, then the integral of gradient of this function, then this flux through any sphere around point x will be equal 1. Yes, I have explained it more than once, so let me think that you understand it. And it is one condition, and the other condition is g of x, y, when y is on the boundary, equals 0. Yeah? So if we manage to construct this function, no, we know how to construct a function which satisfies this condition. This is a function which I call fundamental solution. It's function in the whole space. It is either logarithm with some factor, constant factor, or some power of distance from the point x. So y distance between x and y to some power, 2 minus n, with also with some coefficient. But this function is not 0 on the boundary. So we have to correct it. And the problem is how to find this correcting harmonic function. We have to add harmonic function such that the sum will be 0 on the boundary. So I'm going to do it for the semi space, and in this case solution is given by the following formula. U of x equals integral over domain D g of xy f of y dy, it is d, dy, plus integral over gamma here dg of xy d and y times g small of y ds y, the point y, where here ny is a unit external vector n at the point y. So this is the point y on the boundary. And this holds when the function g satisfies these two conditions, condition 1 and condition 2. Now consider the function consider our domain, which is the upper half space. Yes? So suppose we have a point x here and a point y here. Yes? And we okay, I will write here and draw in other place. Let me remind you that the fundamental solution k of xy is the following. It depends on the dimension of this space. It is solution in the whole space. It is 1 over 2 pi logarithm model x minus y if n equals 2. And it is 1 over 2 minus n omega n module x minus y to the power 2 minus n if n more or equal than 3. So what is omega n? Omega n, it is n minus 1 dimensional area of unit sphere in Rn. Unit sphere, I mean sphere of radius 1. Yes? Say in case n equals 3, omega 3 equals 4 pi. Now we can think that cases n equal 2 and n equal 3 are practically the most important cases, most practical. So there is a general formula for omega n, which I don't remember. If you will need it, we will find it somewhere. Okay. And I'm going to use, so our domain D equals R and plus, yes? And I'm going to use the reflection method. It is the following idea. Let me introduce notation. So in R, the n-dimensional space, say x equals x1, x2, xn minus 1, xn, and I denote the first n minus 1 coordinate by x prime. So equals x prime xn. Because these coordinates are coordinates in the plane, which is the boundary, and this is coordinates in the perpendicular. So it is, say, xn it is x prime. Now in two-dimensional case x prime consists on only one coordinate x1. But in three-dimensional x prime is in fact x1, x2. Yes? And correspondingly y equals y prime, yn. Yes? So suppose we have here the point x, here we have the point y, and now let me introduce the point x equals x prime xn, and x bar equal the point x prime minus xn. Yes? It is so it is x, and this is x bar. And now I define the following function. G of xy equals k of xy minus k of x bar y. Yes? So one point, the first term kx1, it is a function in the upper semiplane which has a singularity at the point x. It is a function of y. If we fix x as a function of y, it has singular point here. When you approach this point, our function k, which is here, goes to infinity. And this function, just look, if y is moving in the upper semi-space, yes, then it will never approach the point x bar, because x bar is the lower semi-space, yes? So this means that this function is harmonic function here in the upper semiplane. It is everywhere harmonic. Let me write harmonic. Yes? And so, and now, what happens if y is on the boundary? If y n equals 0, then what we have, if y is here, then the distance between x and y is equal to the distance between x bar and y. Yes? Then module x minus y equals module x bar minus y. And this means that these two terms are equal because this function depends only on the distance between x and y, and the difference is 0. So g xy is the Green's function in Rn plus. Yes? And so we can write the formula u of x equal integral over Rn plus k of xy f of y plus integral over r n minus 1 dg of xy dn at the point y d x prime. X prime, it is x1, x2 to till xn minus 1, which vary in the plane Rn minus 1. So x prime is coordinates. Now the first thing, what is derivative that is in direction of external normal? Let me draw the picture here. So it is x prime, it is xn, or better y prime. Y prime, yn. Yeah? And our domain is this. And the external normal looks down because it should go out of our domain. So it is ny. This is the point y. If it goes down, this means that this derivative is inverse, it is minus derivative of this function with respect to yn. Which is equal, so let me write, I don't want to be lazy. U of x equals integral over r and plus g of xy f of y dy minus integral over r n minus 1 dg of xy dyn dy prime. Yes, so this is the formula for solution. And now we have already the expression for g, we have expression for k, and so we have expression for g, and we don't have still now expression for the g dy, but we can do it. We just differentiate the function g. So let me do it. Let us consider separately case 2 dimension and more than 2. So n equal 2. Then our function g of xy equals 1 over 2 pi logarithm model x minus y minus logarithm model x bar minus y. No, equals 1 over 2 pi logarithm x minus y. Let me write 1/2 logarithm x1 minus y1 square plus x2 minus y2 square. 1/2 to make it square root of this, plus, I'm sorry, minus 1/2 logarithm x1 minus y1 square plus, and instead of x2 I have to write minus x2 because this point is lying in the lower and minus x2 minus y2 square. Okay. So this is the Green's function. Now we have to differentiate with respect to y2. dg of xy dy2 equals 1/2 pi. So how to differentiate this? We have to 1/2 2. Here we have to write x square minus x1 minus 1 square x1 minus y1 square plus x2 minus y2 square times derivative of this 2 minus 2 x2 minus y2. Yes. Minus 1/2 here x1 minus y1 square plus no, I can anyway this x1 plus x2 plus y2 square times 2 x2 plus y2. Now let me now find it when y1 equal 0, y2 equals 0. dg of xy dy2 y2 is 0 equals 1/2 pi. So what is here? 1/2 times 2 x2 minus y2. Simply minus x2 yes, x1 minus y1 square plus x2 square equals y2. And here again minus x2 times the same. So minus 2 x2 equals equals minus x2 x1 minus y1 square plus x2 square equals simply minus x2 divided by module x minus y square. And now dg of xy dny for y2 equals 0 equals minus dg of xy dy2 y2 equals 0. Yes? So it is equal to with plus. One moment, I forgot 1 over 2 pi. 1 over 2 pi times 2, so it is 1 over pi. Minus 1 over pi equals 1 over pi x2 module x minus y square. Yes. So we found this quite simple formula. And now we know what to substitute here. And I want to consider the case of the following problem. I would say reduced Dirichlet problem. We consider equation delta u equals 0 in R2 plus. Yes? And u for x2 equals 0 equals g of x1. Yeah. So we are looking x1, x2. We are looking for a function which is harmonic here in the upper half plane and takes given values at the boundary. Yes? So we consider this function. And then we can write the solution u of x1, x2 equals integral, I write from minus infinity to plus infinity because it's integral along just this line, this x1 or y1 axis. X2 divided by x1 minus y1 square plus x2 square g of y2 or y1 u of x1, x2 equals 1 over pi integral from minus infinity to plus infinity. Here it is x2 divided by x1 minus y1 square plus x2 square, g of y1 dy1. Yes? Let me, for a minute, for some time, stay with n equal 2, because we can see a lot of things here which are common to any n. So for other n I will do it closer to the end. Let me denote this function which I found here, h of xy. Yes? Now in this case, h of xy equals 1 over pi x2 modulo x minus y square, or what is written here. No, let me write to be consistent. x1 minus y1 square plus x2 square. Now here x is in the upper semiplane, here is x, and y is on the boundary for x2, y2 equals 0. Okay, and let us consider the following thing. We solve this problem, this Dirichlet problem, where we have something on the boundary, and the function should be harmonic function. And let us consider the simplest function on the boundary, simplest function g. Do you know what is a simplest function? Which function is the simplest whatsoever? Yes? Of course it is delta function. Yes? So imagine that you have the function g, it is the y1, is the axis y1, it is 0, and suppose we have the function like this. Yes? Now, if it is a function whose support where it is non-zero is from minus epsilon to epsilon, yes, and when epsilon goes to 0, and the integral of this function, this area, remains equal to 1, then in the limit when epsilon becomes 0, we have delta function, yeah? So suppose g of y1 equals delta of y1, delta function which is unit mass at 0. And just substitute it in this into this formula. Then u of x1, x2 equals integral from minus infinity to plus infinity x2 x1 minus y1 square plus x2 square delta of y1 dy1. Yeah. So this is this formula. Now here we integrate along the axis y1. x1 and x2 are constants. So let me temporarily say that this function is, say, function phi of y1. So it is integral phi of y1 delta of y1 dy1. We know what it is. It is equal to phi of 0, simply so. We take this function, multiply it by function phi of y, and it is something like this. And the result is the value of this function at 0 if you multiply. Because for any for small epsilon, it will be close to value. It will be some integral or over some small neighborhood of 0 with weight whose integral is 1. So the result is closer and closer to value phi of 0 when epsilon goes to 0. And so now what is phi of 0? I have to substitute here y1 equals 0 equals 1 moment, 1 over pi equals 1 over pi x2 x1 square plus x2 square. Yes? You see this function. It is, and this is exactly h of x1, x2, 0. This. No, first of all, this function is harmonic. Yes? Delta h with respect to x equals 0. No, you can we can do it. Let us find it is important point. So that definitely is the function h of x1, x2, 0 is everywhere positive in R2 plus. It is positive function. 3. This function is has the following property: integral from minus infinity to plus infinity h of x1, x2, 0, dx1 equals 1 for any x2, positive x2. No, it is exercise 1 over pi integral x2 x1 square plus x2 square dx1 equals 1 over pi integral. Let us divide it by x2. Let us divide it by x2 square 1 over x2 integral from minus to plus infinity dx x1 x2 square plus 1 equals 1 over pi integral, say, dt 1 plus t square. So what is t? Equals x1 x2 dt equals 1 over x2 dx1. Exactly what is here. So it is equal 1 over pi arctangents t from minus infinity to plus infinity. Yes? No, which is equal 1 over pi times pi equals 1. So we find this. And next, the last thing that if you consider, I would say, integral where is h? Here is h. Integral from, say, minus epsilon to epsilon h of x1, x2, 0, dx1 equals, integral, so 1 over pi x2, 1 over pi x1 square plus x2 square dx1 from minus epsilon to epsilon. And now if you take t equals x1 by x2, it is equals 1 over pi integral, so t is x1 over x2 from epsilon over x2 from minus epsilon over x2 dt 1 plus t square equals 1 over p arctangents t from minus epsilon over x2 to epsilon over x2. If you fix any epsilon and x2 goes to 0, then this goes to minus infinity, this goes to plus infinity. So it goes to 1. Yes? So the mass of this function, when we go closer to the x1 axis, when you go closer to the x1 axis, and it is x2, this function becomes closer and closer to delta function, I have to see, because this function is positive and its total mass is one total integral, and integral over a small segment from minus epsilon to epsilon goes to 1. So integral outside goes to 0. So this means that when we, if you consider this function on the line x2 is constant, if you consider this function, so for say x2 equal 1, it is looks like this, yeah. For x2 equals, so x2 equals 1. For x2 equals 1/2, it is if you have x1 as 0, it is 2. Yes, so it is like this. No, like this, and so on. The smaller x2, the higher this peak and the narrower this peak. So we see yes, we see that this is goes to delta function. To delta function. And the last is the following. The function h of x1 minus y1 x2 this function, y1 is here, is just moved function, yeah? And on the boundary, this function is for x2 equals 0, equals delta of x1 minus y1, yeah? And we can write g of y equals integral delta x minus y g of x dx. Yes? So we can compose our function g, represent this function as integral of delta functions. So we have many delta functions with this weight g of x, and they will, so it is x1, and they together, this integral of them gives us the function g of y. And so this is elementary solution, yes? Elementary solution, the simplest solution, which satisfies a boundary condition that on the boundary it is delta function. Yes, and now shifting this solution right and left and multiplied it by corresponding function g, and then integrating, we have any other solution, a solution of the Dirichlet problem. That's it. So this is the meaning of this function. So we are able to solve the Dirichlet problem in half plane. Now, for now it is in half plane for any for any boundary function g. And now it remains to find the similar function h in any dimension. So n more or equal than 3. And our function g of xy equals k of xy minus k of x bar y. X equals x prime xn, x bar equals x prime minus xn. Now k of xy equals 1 over 2 minus n omega n model x minus y 2 minus n to the power 2 minus n. This is k equals 1 2 minus n omega n x prime minus y prime square plus xn minus yn square to the power 1 minus n over 2. And so we have g of xy equals 1, 2 minus n omega n, and here you have x prime minus y prime square plus xn minus yn square to the power 1 minus n over 2 minus x prime minus y prime square plus minus xn minus yn square, but let me correct it. It does not change nothing if you change sign under the square to the power 1 minus n over 2. So this is our function. Now we have to differentiate it with respect to yn. dg dyn equals 1 over 2 minus n omega n. Let us write here. So here 1 minus n over 2. This is x prime minus y prime to the square plus xn minus yn square to the power minus n over 2 times derivative with respect to yn xn minus times 2 xn minus yn, but it is minus 2 minus 2 xn minus yn. Yeah, it is one term minus what is written here, 1 minus n over 2 x prime minus y prime square plus x n plus yn square to the power minus n over 2 times derivative of this times 2 xn plus yn. Equals no, and now let us find it at yn equals 0. dg dyn, so of xy, for yn equals 0, equals the following. So it is here minus 2, again 2 times this, it is 2 minus n divided by 2 minus n omega n, and here it is x prime minus y prime square plus xn square, yn equals 0, minus n over 2 times 2x minus 2 minus xn. 2 is already here. Minus again the same factor, x prime minus y prime square plus xn square all to the power minus n over 2 times again xn times xn equals minus 2xn minus 2xn divided to minus n to omega n minus xn, yes, times in x prime minus y prime square plus xn square to the power minus n over 2. But now let us see that it is simply x minus y if y is on the boundary. So it is x minus y square of the distance to the power minus n over 2 equals minus 2 xn omega n module x minus y the power minus n. Here y n equals 0. Don't forget about this. And the last stroke is that one moment. dg xy dn at the point y equals minus dg xy dyn. Yes, if yn equals 0. The same picture. It is the upper hemispace, and y looks out of this domain, so it looks down. So we have to change sign. And this means that dg dny equals 2 divided by omega n xn modul x minus y to the power n. Now, in particular, for n equals 3, let us see what it is. Omega 3, it is the area of unit sphere, two-dimensional unit sphere in three-dimensional space. It is equal 4 pi. And so 2 divided by 4 pi, so dg dy n equals 1 over 2 pi, 2 over 4 pi, x3 divided by x minus y cube. And again, this function, let me denote it as again as h of xy. When we go closer and closer to the boundary, this function becomes closer and closer to delta function. Yes? And again we can write, but we have this formula already. It was obtained independently, that if you consider the problem delta u equals 0 in R n plus, u on R n minus 1 equals g of x prime, yes, then we have the following formula: u of x equals integral over R n minus 1 h of xy, so y in R n g of y dy. Similar thing. Let's see it. So this is the general formula in any dimension. Now we have this formula for, it is formula for n equals 3. So we can solve it. In fact, it is interesting to consider different particular cases. We can solve, really solve some simple equation. The problem reduces to find this integral. No, I hope to have some tutorial with you where we consider some simple problems like this. So for now, let us finish. Have a good time. Bye.